Thank you very much. Good morning. Happy to see some faces here. It's still very early, so well, let's go. My name is Niels van Dijkhuizen. I also go by the nick of Nebula. I work with a CSERT in a large organization in the Netherlands. Well, I like to tinker with electronics. I'm a demo senior as well. In my spare time, I do some research, and I want to show one of my projects. The project originated from some pen tests, where I got some obstacles, and that's why I thought of this project. And I wanna ask you something. How many of you have active protection on some USB attacks on your laptops? Please raise hands. Nobody? That's interesting. There are quite some attacks. The purpose of the presentation is to raise some awareness again. We already know that there are some attacks available. Of course, you're not the average person. You know something about security. But still, let's see what we can do. Oh, I forget to mention the agenda for today. We start off with some attacks that you probably already have heard of. What's wrong with them? The available protection mechanisms. And then we'll talk about my implant and what it's tried to achieve. So, short history. The oldest reference I could find on USB keyloggers was from 2005, the key host. If somebody knows an older reference, please let me know. Then 5 years after that, 2010, we get FUCT, which is a programmable hit USB keyboard dongle from Adrian Crenshaw, also known as Iron Geek. Hack.5 also created the rubber ducky back in around the same time. They are both based on TNC2 microcontroller. And in 2011, Adrian enhanced it a bit by combining it with a keylogger. And my presentation is also combining the two things, so sniffing and injecting keystrokes. But it has some other accents. In 2014, BadUSB was presented by Carsten Knoll, SR Labs in Germany, which explained manipulation of firmware to get new functionality out of ordinary devices. And this was also shown by Adam Kudrill and Brandon Wilson with the Psychon implementation. Same year, Semi Chemical showed his USB drive-by, which just added mouse support, mouse emulation on top of the keystroke injections. In 2016, we've seen a paper from David about, well, he calls it BadUSB 2. Essentially what he does is to take two phase dancer boards with a mediating machine to get a man-in-the-middle attack on low-speed USB devices. And this year we've seen the Bash Bunny, which is essentially a rubber ducky on steroids with well, let's say a programmable BadUSB, and the Cactus Wi-Fi hit injector, which is a keystroke injector with Wi-Fi support. So what's wrong with them? Well, they're kind of in your face. If a user sees the computer doing weird things, well, they might throw out the device, they might shut the machine, they might go to somebody with IT security knowledge. So it's not very stealthy. So in order to make this kind of attack work, you either require an unlocked and unattended machine. You have to do some good social engineering with quite some distraction to get the opportunity to get a payload on the machine. And many of the payloads we've seen for the injectors are depending on payload from a network, mostly internet. That's not always accessible. I mean, enterprises can have something like a Citrix farm with internet connection and not the endpoints itself. And there are protections available. We can do class filtering, etc. So that's what we're going to look at now. We've seen Robert Fisk's USG and Dominic Spill's USB proxy. Both are external devices that you put in between your device and your host. And the first one allows to act as a bit of a firewall, USB firewall. But it's okay conceptually. So it doesn't allow a re-enumeration of devices. So if I have a mass storage device and at some point it reconfigures itself as a keyboard, it will detect it and will block this behavior and it will just shut the port. And it does basic some basic class filtering. Unfortunately, it's very slow. It's not even, I mean, it's USB 1 speeds, but it's slow. It's too slow for practical use. You cannot transfer big files over it, for example. Dominic Spill is still work in progress, the USB proxy. At the moment, write blocking to my storage devices to stop exfiltration, data exfiltration. Then we have the middle group, which does class filtering, essentially. USB Guard is a pretty good example. It's a Linux implementation done by Daniel Kopecek from Red Hat. It's very fine-grained. You can even fingerprint the device because it hashes the table descriptors and the report descriptors. So if you have a device with a different serial number, it will notice it will not allow that particular device. So you can really do good black and white listing on USB devices. GoodDog, BeamGun, both Windows tools, they accept only certain types of devices. And then there's GData's USB keyboard, keyboard guard, which just gives a pop-up when you plug a new keyboard in your machine. Is this a real keyboard, yes or no? Then you have to answer as a human. Then there's Duck Hunt from Pedro M. Sosa. This is a Windows tool as well. It will monitor for superhuman typing. As soon as it sees superhuman typing, it will just get the focus away from the object and it will block the attack. And finally, GR Security has a nice patch that allows only devices connected at boot time to be connected. Everything plugged in afterwards will just not be accepted. So there are some protection options available. So my implant tries to do things differently. I want to have a hit attack that works with locked machines and bypasses known protections. Furthermore, I'd like it to be affordable, small, and covert. Well, how am I going to do that? Well, the implant should be in line with the keyboard and the host. This way, I don't have to deal with the re-enumeration. I can do credential sniffing. I can monitor activity of the user. And this allows, I mean, the second one is the implant should have notion of real time. And this allows for programming of the attack time frame, which can be convenient. And to spice it up a bit, it would be nice to have some means of remote control. And let's do that over the air in local communication so that we can do remote sniffing and controlling. Will not be this small, no, not the cotton mount size. So this is what the hardware diagram would look like. we start off with a USB host controller. I based mine on the Maxim chip that connects the keyboard with the microcontroller. The microcontroller is a TNC2 because it's nice and tiny and it's easy programmable. That connects to a Maxim real-time clock, a high precision real-time clock, RTC. And we connect 433 megahertz UART to the controller. And we need some EEPROM for non-volatile memory storage to have a configuration. This is what my proof of concept looks in for real. Could have been smaller, of course, but it's a proof of concept, right? So I can ditch the little EEPROM, the one you see over here. Let's see, the one over here, because essentially the TNCLs already has EEPROM on board, and I don't need the extra space. So if I make my own PCB, I can just stack the TNC and stack stuff on top of each other, and then we'll have a smaller form factor. And this is a photo of it with the lid closed. Some nice LED indicators to see it functioning. So let's talk about bypassing some of the protection mechanisms. USB enumeration essentially is the process where you check the device. You ask for a blob called a descriptor to see what the device actually is. It describes itself to you so that the host knows, okay, this is a mass storage device from a certain brand. So what we have to do, we have to clone those descriptors in order to bypass the class filtering or the black-white listing that we saw with the USB guard, for example. So that's exactly what I did. It was a bit of a hassle because at some point I had to figure out the device, the TNC presented itself as a USB 2 device, but a keyboard is a low-speed device, as you might know. So, but it's really doable. It's quite easy once you know how to do it, and then we have to bypass the superhuman typing speeds. Well, that's quite easy, right? We just have to throw in some tens of milliseconds in order to look like a human. So I created my own Arduino device class to get both done, to do the device cloning and the normal typing. Well, that's the speed a normal key injector works with, so it's quite fast. And if we use the class I created, we just get slow speeds, that's all. Dum-ti-dum. So that way we can bypass duck hunt, for example. Then we have to take the power consumption into account as well, because we cannot use too much current, of course. So we have to draw all the current from the host. Sorry? Not that I am aware of. I think that would be interesting indeed. That then you can profile. The question was, can you monitor that from the OS operating system? And that would be a good approach, I think, to see whether there's something in between and have a profile for every device. As you can see, the differences aren't that big, except for the peak power current consumption. When the Keynterceptor is in between, it's 40 milliamps more at max. So when it's fully, the transmission costs some energy. So but it's still within the boundaries that the descriptor is describing to the host. The keyboard I cloned was allowed to use 100 milliamps, and I just got there, so it's okay. I think I'm still within the specs. So the bill of material, the cost, well, it's really affordable. This is just common off-the-shelf stuff. If I would make my own PCB and solder on my own chips and bulk order the chips, I can get the price lower, of course. I think $35 or 30 euros is still acceptable. So here we have it. It's a small and cheap or affordable device, which is quite hard to detect from the host side. It can bypass protection mechanisms because we clone the descriptors, we type like a human, and no enumeration is needed because, well, it's part of the keyboard. Whoops. We can think of different use cases for the Keynterceptor. We can control over the air. We can auto log in with captured credentials. We can inject keystrokes after a chosen time frame. Block the user's input, so essentially used as an RF kill switch. Insert your scenario here. My scenario is the following. I made a companion for Keynterceptor. I built it into a power block. The power cord that you see there is not a regular power cord, it's a UTP cable. And inside is a little power supply with the NanoPi Neo, a small Raspberry-like device, which has a 4G dongle connected on it and a 433 megahertz transceiver. And this is how it fits in. We have carrier-grade netting, of course, because most operators, mobile operators, will do carrier-grade netting. Therefore, listening services will not work. IPs will often change, so that's why we need a VPN. So just put a VPN server on the internet, connect from the companion to the VPN server, and you can do the same with an attacking laptop or mobile phone, and then that way we can connect to it over the world. And the advantage of this is it's less detectable than Wi-Fi. You will easily find rogue Wi-Fi access points. It's a bit harder with 4G. And then the Keynterceptor and the companion are talking to each other locally over 433 megahertz. So, demo time. Let's see. Yeah. So we have a regular office with a computer, and we start to plug in the companion because it takes a while to set up a connection to start the VPN. In the meanwhile, we get the Keynterceptor. And if you do pen tests or red teaming or something like that, I would advise to pick a machine that's on the desk because it's easier to access. This way it takes a bit of time, sorry. Okay. So, at some point you will see the companion LED blink. That's an indicator that it's waiting for a configuration to receive from the, did I say companion? The Keynterceptor is blinking to receive a configuration file from the companion. So I start the VPN on my mobile phone, and then I can access the web interface via web app. And at this point you will see ETH0 is not yet defined, it doesn't have an IP address, so I connect connect it to the local network. We get an IP address, and then we are able to either put it in demo mode or timed mode, and set the start and the stop time when it can be active. And then we send over the IP address and both the period in which it can be active. Now the LED is stopped blinking because it received the configuration, which is stored in the EEPROM. So if I disconnect the Keynterceptor and reconnect it, it will still have the configuration. So we put away the stuff, so it's not inside. Unfortunately, the companion didn't fit between the desks, but you get the point. So somewhere else, different location, I have a tethering, started tethering, and I set up a VPN, and you just SSH into the companion, start a listener at the left, start a keystroke monitor or snooper at the right to see what the victim is doing. Right. So we see the user being active on his machine, and we see the keystroke sniffer on the right side. So everything is transferred over the 433 megahertz connection. So at some point the machine gets locked, the user has to go to the toilet, for example, returns, enters his password, and the password is captured by the Keynterceptor. Okay. In the evening, if the person leaves the machine on, we get into the active time frame, 20 minutes of inactivity. The Keynterceptor just logs in to the machine and starts to type PowerShell commands to retrieve the payload from the Keynterceptor companion, from the companion. And this way we get a shell to the companion. And since we already have a connection to the companion, I can take over the machine. Start doing lateral movement and that kind of stuff. There we go. I've got the local IP address and the listener, and we can see top secret was the password typed by the user, and the machine is popped. So we're ready to go. So is this realistic? I think so. It took some while to make it and test it, but I think if I can do this, not everyone, but I think a lot of people, everybody could do it. So there's some future work. I might try to fit it in real hardware. Have automatic description, automatic descriptor cloning. At this point, I just cloned it. Was some manual labor. And finally, encrypt over-the-air communication, because this was just decoding. The downsides of this approach is it needs good mobile coverage. I also have a companion which uses Wi-Fi, but well, still need to take that into account. You need some time to deploy, more time to deploy compared to a standard keystroke injector. Yeah, and of course the user has to leave the machine on within the time frame, the detect time frame. So I think that's my presentation. I hope the industry will come with some solutions, because we really cannot trust our devices, right? So, not the USB device, at least. That's my presentation.
Okay, questions without bribing with Mate? Any questions?
How did you manage to get the 433 megahertz connection reliable? Because there tend to be a lot of crossfire on those things, key fobs, weather stations, stuff like that. And if they insert into the computer, that might be a bit weird. Okay, well, I had very good coverage with 433 megahertz, much better than the 2.4 gigahertz Wi-Fi. So, and if you have a good line of sight, you can configure it this way, that you can get over, I think, a kilometer of, yeah. I didn't put it, I configured it this way that the companion and the Keynterceptor would be in the vicinity. But mostly, if you have an office building, that's doable, and the communication was pretty stable. So, if you want to know, it was the HC12 module, Chinese thingy. And what did you do encoding-wise? So, why did I do it? Encoding-wise, so how did you encode the letters and so on? Is it just a serial connection? Yeah, so start character, the ASCII value of the scan code value, I guess, and a code to verify that was a key press. Quite simple.
Okay, so first of all, this is a fantastic project. To answer the previous question, people scan frequencies, and the 2.4 is something people will look for, not so much the 433, exactly because of all the noise you said. What I could suggest though, is that you don't keep the link active at all times. If you can do burst transmissions, then that is the best solution. Obviously, I think, so we mentioned the power consumption, so that could be an interesting gauge. And also, so the installation is complicated. If you make it a lot smaller, then that would be great. But then, not sure there's much to do with it, but a USB device disconnect and reconnect would always be one of the signs, right? Because you have to put it in the middle.
Reconnect, yeah, but so if an attacker just turns off the machine, yeah, put it in between.
Well, if you put it when the machine is turned off, then no one can ever detect that. But if you install it on a running machine,
yeah, true. But since it really looks like the same device, so okay, true. And there are some other things you could do. Of course, you could for example, limit the time that the machine is allowed to stay on after user has locked the machine, right? I mean, that's another thing you could do.
Yeah, so that's OPSEC.
But yeah, you could detect plugging, unplugging, but in real life we sometimes unplug our keyboards, right? So, yeah.
Thanks.
So, what is it that we can do against this? Is this completely undetectable? Is there nothing that we can do to defend against this?
Not much. I would say it would be very well. What you could do, of course, is have a CAPTCHA, for example, at the login screen or something like that, or two-factor authentication. It's a bit of a hassle, I know. Every time you lock your machine, you have to go through this process of typing extra stuff or clicking on something. But I think it would be good, a good design for an operating system to include such options.
Like the Bluetooth keyboard pairing.
Yeah, exactly. Like Bluetooth keyboard pairing, as the man in the fro say, whatever.
Any more questions, comments?
No more questions?
No?
Thank you.
Thanks very much, Niels.